report. The purpose of this lab was to create a model where we had an object in free fall motion where it's dropped from rest and falls straight down. We used Tracker to create a position versus time graph for the observational model, and GlowScript to create two computational models where there's differing net forces. We used the momentum principle, which we did use the last lab, and figured out that it could be rewritten into this equation, but due to Fnet equals ma, we can rewrite this term to equal the force of gravity. And then for the position of the object, we're going to have to use kinematics equation because it is projectile motion, and the generalized formula is this, but obviously since we're only talking about the y component of displacement, we can change it to this. And then overall, the results were fairly similar, but again, they had slight differences due to initial errors in the lab. So the experiment was that a paper ball around 5 grams was dropped from the height of my door, which was about 2.03 meters. And then, like I said, using Tracker, an observational model was made, and using GlowScript, two computational models were made. One only included the force of gravity, and one included the force of gravity and the drag force. I use this model because it's just very simple, and if there's any difference in the results, then I could look back on the calculations and know where it came from fairly easily. As well as if I had a perfect spherical object, then there wouldn't be much drag force, so I used a loosely crumpled ball to ensure that there was drag force. There's no initial velocity, and the initial position is 0 because I set it at the origin in Tracker. The time interval was 0.7 seconds, and then the mass of the object, as I said, was around 5 grams or 0.005 kilograms. The system was the paper ball, and the surroundings were the space-set air that implemented the air resistance and gravity on the ball. There's two initial errors, and they kind of tied into each other. With the observed model, obviously you have human error and variation where you don't have perfect freefall motion. However, the computational model is assuming this, and it's assuming that all the forces you put in are the only forces acting on it. So the errors in the observed model led to errors in the computational model because we didn't code for all the forces present. Within the coding itself, there wasn't much changed. Obviously, the mass had to be changed right here, and then the initial position and velocity, as well as I just made like a gravity vector because it was just easier to have a vector and then a magnitude to plug into the equations. And then the while loops time was changed, and then the equations for the final velocity and final position would change to match our principles shown above. And then the drag force was set here, and then it's created down here as the Fnet is equal to the force of gravity plus the force of drag force. And I'll get into the details of that now. So as you can see, all three position versus time graphs are very similar. The only difference is in the displacement, which makes sense because the computational model doesn't know that the floor is there. So the displacement they go in the time interval will really tell the difference in the forces acting on it. So the observed model only fell 2.3 meters since that was the height of the door. However, the computational model with only gravity predicted 2.4 meters. So obviously it's not accounting for another force upward that's making the object fall less displacement or distance. And then the second computational model, it was closer, but what I realized is that even exponentially raising the B value of the drag force, it still wasn't enough, and it eventually capped out. So the closest I could get was around 2.36 meters, which is still close, but it still shows that there was other forces present in the observational model that we did not specifically code for. As I said before, those are the initial sources of error in the lab, is just that the observational model, all of its forces are not accounted for in the computational model, and thus we can't get a perfect computational model to match the observational model. Like I said, the goal of this lab was to find an object in free fall and compare its models. As you can see by the position versus time graphs, we did have an object in free fall, but due to the initial errors in the lab, the results did differ. For the what if, what does it mean? Did any of the models capture terminal velocity? And terminal velocity is just when you reach the maximum velocity where the force of drag is equal to force of gravity. And on a velocity versus time graph, it would show a linear slope downward. This was slightly seen in the first model because there are points where the velocity was linearly downward in slope, but it didn't really follow it perfectly. And in the second model, it didn't follow it at all. Actually, the velocity versus time and the position versus time had a very similar curvature. But again, each model didn't predict terminal velocity in my case. And then what if the ball was thrown downward with an initial velocity? This would not change the terminal velocity. Terminal velocity is more of a set value, and if an object is thrown faster or slower from rest, then it will just return to that value.